Section 27, integrating with substitution. All right, this is a pretty important section. Just like the chain rule was very important in derivatives, the substitution method is super important because it's how we undo the chain rule. So they're important for like the same reason. Forwards, backwards. The way we end up doing this is we have some sort of composite function here when we take the derivative of a chain rule thing. This is the like chain rule equation. If we have two functions, one embedded within the other, when we take the derivative, we take the derivative of the outside with the inside plugged in and multiply by the inside. So this is what's meant by composite function. To undo it, we say, hey, this was the thing we took the derivative of, g of x. It turns out the derivative of g of x is g prime of x, which hopefully you know, and this matches perfectly with what we got here. And so when we go to rewrite our integral, all we have to do is say, hey, we're taking the derivative of the outside function, we're integrating the derivative of the outside function with the inside function times the derivative of the inside function. And in this format, it's much easier to integrate. Let's look at some examples for how to do that in just a moment. The steps for every one of these problems is to find the u and du combination that will allow you to simplify the integral. In this case, it was just picking out that u was the inside function and du perfectly matches what's here. Plug u and du into our formula. That's this step. Integrate with respect to u. That's this step. And then plug in what u is equal to. So our last step after this would be to say, hey, our answer is f of g of x plus c, which matches our original starting thing, which was f of g of x. All right, now example with numbers. Let's go to the back side. And here, we have a perfect u and du pair in this one. This one's a nice problem. So our u is 5x cubed minus 3x squared minus 7x plus 4. And I chose that because this thing's derivative is right here. Also, this thing is raised to the 6th power, and if that was our du, that'd be ridiculous. We'd have u times the u to the 6th power. We can't deal with raising our d whatevers to powers in substitution problems. And so if you have something that's raised to a crazy power, you either need to expand it or you need to use u substitution to plug in u for it. So our derivative of this is, well, conveniently, we can either just take the derivative of this here and we get this, or we could just say, hey, it is exactly just that. So now our du is just equal to this stuff, which is 15 minus 6x minus 7 dx. Where the dx comes from is the fact that when we take the derivative of u with respect to x, we get du over dx equals that stuff, and then we multiply the dx to the other side to get it to match the integral form. All right, now we rewrite our integral. We just get, well, the inside's just u. So u to the 6th. And it turns out this stuff at the end, that's just du. We figured that out. It was just du. Okay, one tripping point for a lot of people is the fact that du has both x's and dx in it. This is okay. Remember to think about du as what the chain rule part is. So the part that we took the chain rule on, like that derivative section, that is what du should be. So we should have x's and dx's in it when we have complicated insides like this one. So that's totally expected and good. The integral of this is just u to the 7th over 7 plus c, and then we just plug in what u is, which is 5x cubed minus 3x squared minus 7x plus 4. And you get the answer. So it's really nice in cases where this matches perfectly. Let's move on to another case. We're moving on to the case where I want to wait to do this problem because this problem's like the hardest kind. So let's do like an intermediate here. Let's do the integral of negative cosecant squared x cotangent x dx. I'll admit this maybe not a medium problem, maybe a medium hard problem. So the key here is to recognize derivatives of things. There are actually two legitimate options for u substitution here. There's one where you say, hey, u is equal to cotangent x. And if I pick u as cotangent x, then I get that du over dx is equal to negative cosecant squared x, which happens to match perfectly what's in our function, because that is the derivative of cotangent of x, is negative cosecant squared x. And in this case, when we multiply the dx over the side, we get du is equal to negative cosecant squared x dx, which matches perfectly with what we have here, and we'd rewrite our integral as u du. Because cotangent of x times negative cosecant x dx is exactly what's up here. Cotangent of x, negative cosecant x dx. All right, the other option here, equally legitimate, is to say u is equal to cosecant of x. And you may remember that the derivative of cosecant x is negative cosecant x cotangent x. And if you notice, this times this gives us exactly that, which means this is a legit method here. And if we use this technique, well, we just get this times u du again. Cool, so no matter which technique we get, we simplify to something really easy. These integrals are very easy. U squared over 2 plus c, u squared over 2 plus c. But when we plug back in what our u was, we're going to get two different equations here. We're going to get a cotangent squared x over 2 plus c for this one, and we're going to get cosecant squared x over 2 plus c for this one. It turns out that these functions are exactly the same, except they're phase shifted. They're slightly shifted over. So our c values would be different for these if we were given a point. Like if I said this graph went through 0, 1. The c value for this problem would be different than the c value for this problem. That's it. These are both correct answers to that problem. All right. Weird, right? Two different answers, but if you remember, sine of x is always equal to just cosine of x plus a phase shift. And the phase shift where these guys match up again is just all you have to do to cosine is you have to shift the x over to when it starts. So sine starts at 0. So you want to shift your cosine over to where it starts at 0 and heads in a positive direction like sine does. So we actually subtract pi over 2. And this is always true. You could rewrite an entire function or expression full of sines and cosines just in terms of sine or cosine just by using this property. All right, enough on that. Let's do our last substitution problem. This is the one where it's like not our normal way of doing substitution problems. This is one where the derivative of the inside of our function here is not equal to our thing on the outside. Like the derivative of 1 plus x is not x squared at all. However, we still use substitution here because there's no way for us to like distribute this in to like a half-powered function like this. So we set u equal to the inside because we want to make that part simpler. We take the derivative of both sides and we get du equals dx, or d over dx equals 1, and then move the dx over. And this may not look useful now, but we also do this little extra thing where we say, hey, if I do this, I'm going to be able to rewrite this part of my equation in terms of u's. But I still need to worry about the x squared part. So I should just solve for x in my u equation. If I solve this equation for x, I get x equals u minus 1. and now I can rewrite my equation in terms of u. So I'm going to do that. Integral from -1 to 0 of u minus 1 squared, which is what x squared is, times, this is the square root of u, and this thing was exactly du, because du is equal to dx. Now, this may not look simpler, and it isn't yet, but we're going to be able to make it simpler because we can expand u minus 1 squared, where we couldn't expand the square root of 1 plus x. So here we get integral from -1 to 0 of u squared minus 2u plus 1 times the square root of u du. And now I can distribute this guy in. Remember, there's no product rule in integrals, so we had to do all this stuff in order to actually do this problem. The integral from -1 to 0 of u to the 2.5 minus 2u to the 1.5 plus u to the 0.5. Again, I have not taken a single integral. All I did was distribute u to the 1/2 into all these terms. Oh, du. All right, now since I've sadly run out of space, I'm going to continue down here. I'm going to integrate this. So I'm going to be plugging in -1 and 0 for u to the 3.5 over 3.5 minus 2u to the 2.5 over 2.5 plus u to the 1.5 over 1.5. Okay, one dangerous and easy to make mistake is to plug a -1 and 0 right here. For that reason, a lot of people, when they're doing these problems, once they've done the u substitution, they write like x equals 0 and x equals -1 to remind themselves that they can't plug that in for u. And so we could go through this problem and do all this. And this might remind you at this step to go, oh, I should rewrite this in terms of x now. So I need to plug in 1 plus x every time there's a u. So I'm going to do that. 1 plus x, the 3.5 over 3.5 minus 2, 1 plus x, the 2.5 over 2.5 plus 1 plus x to the 1.5 over 1.5. And I'm still plugging in -1 and 0. But now I don't need to like put the x there because like I know they're x's, and so this is I can plug in stuff now. If I plug in 0, I just get 1s in all the parentheses. So it's just 1 over 3.5 minus 2 over 2.5 plus 1 over 1.5. And if I plug in -1, I just get 0. So this is the answer, is this stuff. This is why above here I just put these in terms of whole power fractions, like 2 over 7 minus 4 over 5 plus 2/3. So just rewriting them. And then I had to find the least common factor. Turns out these are all like prime numbers, so they have no like easy prime factorization. We actually just have to go to 3 times 5 times 7, which is 105 for the lowest common multiple, least common multiple of all these. So if you do that, 7 goes in 105 15 times, so it's 30 over 105 minus 84 over 105 plus 70 over 105. And if you add these together, you just get 16 over 105. If you're like, this is awful, I don't want to do this, like, this is a pretty acceptable way of leaving your answer on a quiz, this is a pretty acceptable way of leaving your answer on a quiz, this isn't, and neither is this, but yeah, that's where we're at on this. And that's it for substitution.